Today's lesson is the beginning of Chapter 2. Chapter 2 is about variations in graphs, and our discussion today will be about the first type of variation called direct variation. You can see our goals. We have several. So let's get started with some definitions about direct variation. We have lots of different types of variations. Our first type that we're going to study is called a direct variation. It is an equation in the form y equals k x to the n power, where k cannot be 0 and n has to be greater than 0. Now, a couple things. K cannot be 0. If you look at this equation, if k was 0, this would then wipe everything out in this right-hand side, and we'd have y equals 0, which is a horizontal line. We wouldn't have any type of variation going on. That says n is greater than 0, meaning all our exponents are going to be positive for the time being. So you can see, if we would read this equation now for meaning, as we talked about in the last chapter, reading things for meaning, not just reading the variables that are there, we would say y varies directly as x to the n. So the equal to becomes your varies, and you can say directly as soon as you see this multiplication combination. It is a multiplication with the constant and that variable. You could also state it y is directly proportional to x to the n power. Now, that k value is called the constant of the variation. It will stay the same as long as you're on a consistent problem. You switch around and do different variation problems, that k value is going to change. K does not have a maximum or minimum. It sort of depends upon the values being used. It does have one qualification here. K is never mentioned when we read the equation. You probably noticed that. So again, y varies directly as x to the n. So we said the y value varies was our equal. We didn't say k, and then we said the variable and its power. Okay, so in reading, we are never going to mention that k value. It is called the constant because it stays constant throughout your entire work with that equation. Now, the first thing we want to do is ask a few questions based on the definition we just gave you. Is this an example of a direct variation equation? You can see I have 3 different equations up here. And then if you can answer yes or no, preferably yes, then how do you read the following equations? So let's go through and first do that initial question. Is this a direct variation equation? So brain says, last page, we said y equals kx to the n is our basic setup for a direct variation equation. So you would want to compare your equations and say, do they match this setup or do they have some differences? And if they have differences, are those differences so great that it would not allow, by definition, the equations to be called direct? So the first one, y equals 2x squared. When we look at it, it matches almost exactly. Y equals kx to the n. The only difference is k is now 2 and n is also 2. Our power is squared. We did the next one. Difference here, we have a few more we can talk about. Kx to the n is a generic statement. Instead of x and y, so using m and n's, we know that you can switch out variables very easily. We know we can also switch out exponents. And we have 4th power instead of the n. It's okay. We had a squared last time, and now it has to be squared. Squared's an easy one that's very common to see. But I believe, again, that is also a direct variation equation. And last but not least, y equals k x to the n. Start looking at this one. Again, they're using different variables, so c and d, that's legitimate. Our k value is a 1/2, a fraction. If you remember, I did not limit the size of k. It does not have to be a whole number. X to the n, our power of n this time is a 1. And as long as it's positive, which it is, we're good. So I believe all three of these are direct variation equations, and those are some of the characteristics you can look for in identifying your equations. You do need that multiplication look that we have. It has to be multiplied by that constant and the power of x to the n. Now, if we would read these, we showed you on that initial page, there's really two ways. You just are probably going to get comfortable with one over the other. So right now, y equals 2x squared. Think about how you would say it. Does it match y is directly proportional to x squared? If it doesn't, a couple of variations. Y is directly proportional to x to the second power, if you like that better. Y varies directly to x to the second power. Next one. M varies directly as n to the fourth power. Another way to say that, y is directly proportional to n to the fourth power, or you could say y is directly proportional to the fourth power of n. And the last one, C varies directly to D. You could say C varies or is directly proportional to D. C varies directly as the first power of D. So there's not just one right way, but you can see there's some key words that must be used when you're writing these. So read, write, it looked like a normal equation. We're now saying it's a variation. See that multiplier, and you should be able to move through it. Now, in our example in the book, I believe we had the recycling example that said, as the number of cans you collect goes up, your return would be greater. So we would like to say that in all direct variation problems, as x goes up, y, whatever's happening to the result, is also going up. So that's a key characteristic to look at in your values that you're putting into these direct variation equations for your unknowns x and y. Okay, moving forward. Here's an example of a direct variation equation. Now, there's a lot in it, so watch on this first one, and then you'll be able to try one. Y varies directly as x. Write an equation that relates x and y. Then find the value of y when x equals -2. There's several things going on here. The first statement tells you exactly what you have. You should know your equation from there. Then they ask you to write that equation out and then also calculate with that. So, watching this, our given information is x equals 2 and y equals 8. When they say y varies directly as x, you should have been able to say immediately that means y equals kx to the n by definition. And it did not say any power, so we could even go off and say, well, it really means to the first power. And at that same step, I also put in the x and y values that were given. So substitute the given information in. Simplify what you can. So that would turn out basically into 8 equals k times 2 or 2k. We know to undo this. To get k by itself, we would divide by 2. In doing that, we have solved for the k value, which is the constant of the variation. So now whatever we do with this equation, we will be able to use that k value of 4. So what it now means is write the equation that is related. Well, in order to do that, you go back to your situation. Your situation was y and x. So y equals, we solve for our constant, the unknown, and that's 4. So step 1, solve for that constant of the variation. So this is the equation now, y equals 4x, that we get to use for the rest of the problem. So when I say the rest, all we did so far was up through here. We now can do this last part. Find the value of y when x is -2. If we have our generic equation, substitute in the value given, x equals -2 for x, do the math, and you should be good to go, and solve the equation. So we ended up with an ordered pair, if you want to say it that way. When x was -2, y was -8. But with that equation, y equals 4x, you could give countless examples of xy ordered pairs that would now make that statement true. So look carefully back again at what we did. We first identified using the words what type of equation we were dealing with. We substituted in the given information. Once we had that information substituted, we should have been able to solve for that k value. Once you have the constant of the variation, you can write that new equation with the constant in it and use it to solve for any other missing values. That is going to be the strategy which you will use on most variation problems. So let's try one by yourself. Sounds a lot similar to the one we just did, but look carefully. Y varies directly as x. Write an equation that relates x and y. Then find the value of y when x equals -2. X equals 2 and y, or x equals 12 and y equals 2. So solve this. This will be one that we can talk about as we work through it. There are 3 steps we want to remind you of. Find the constant of the variation, write the formula using that constant, evaluate the formula for the given value, and remember, when x goes up in a direct variation, y should also be going up. Last one. In a real-world problem, here's a pizza problem, look at it, that prices varies directly with the square of the diameter. Look at what's here. I want you to work this one out, and we can talk about it and see how well you understand direct variation as part of class. All right? So that's all for now. Try them, bring them to class for discussion. Thanks.